everybody, it's Miss Manelia again, and I'm here to give you a short tutorial on how to perform basic operations using function notation. And so just like with arithmetic, we can add, subtract, multiply, and divide functions. I'm going to start with very simple functions today. I'm going to look at two linear functions. So we're defining f of x to be 2x and g of x to be x plus 1. And so with function operations, I'm essentially just adding, subtracting, multiplying, and dividing these expressions. But it's important to understand the notation. So if I wanted to add the two functions, I can express it either way. I can say it's f of x plus g of x, or I can create a new function called f plus g of x. And both of those mean the exact same thing. Again, when you see those parentheses in this context, we're not multiplying f and g times x. This is just how we express a function. It just means that f and g are the names of our function and x is the input variable. So if I wanted to add these functions, that's exactly what I'm going to do. I'm going to take f of x and substitute in the 2x, and then I'm going to add the quantity g of x. And actually, let me do these in two different colors so that you can see. Sometimes we have to be careful when we're adding functions, or particularly when we're subtracting, multiplying, and dividing. We have to remember that our functions come in quantities. So if I wanted to add my g of x function, I have to remember that it is the quantity x plus 1. Now, since all of the operations in this expression are addition, I know that addition is both commutative and associative, which basically means I can switch around the grouping symbols, I can switch around the order of my terms, and this expression is equivalent to 2x plus 1. And so if I group my like terms together, I've got 2x plus x, which leaves me with 3x plus 1. So addition is pretty straightforward. I do have to be careful, though, with subtraction. So if I take my function f of x, and I want to subtract my function g of x, again, I'm subtracting the entire expression. And that expression, again, is x plus 1. And if I'm subtracting that expression, x plus 1, that means I'm subtracting everything within it. So if I rewrite this expression, I'm going to keep the 2x as is. But I got to remember, having a negative in front of the quantity is essentially the same thing as multiplying the quantity by negative 1. I've got to remember that each of these terms is being subtracted. So this becomes a negative x, and this term becomes a negative 1. And so now when I combine my like terms, 2x minus x leaves me with a single factor of x, and then I still have a minus 1. So be very careful when you're subtracting quantities. You want to make sure that you use grouping symbols appropriately and that you distribute the subtraction throughout the second grouping symbol. Multiplication is the same way. You do need to make sure that you have appropriate grouping symbols. If I want to multiply my function f of x times g of x, I want to make sure that I use grouping symbols. And this time, the grouping symbols I'm going to use are parentheses. But again, in this case, my parentheses correspond to multiplication. And whenever you're multiplying an expression times a quantity, you need to use the distributive property. 2x times x is going to leave me with 2x squared, and 2x times 1 is going to leave me with 2x. And that expression cannot be factored any further. With division, when we get into more complex polynomials and dividing polynomials, we'll be able to actually divide and simplify a little bit further. But for now, there's really not much we can do. If I wanted to divide f of x by g of x, you certainly can use the division symbol, but with division in higher math, we generally use a fraction to denote division. And so I would simply have 2x over the quantity x plus 1. And it's tempting, because you have an x on top and an x on the bottom, to cancel them out and then have a result of just 2 over 1. But when we're dividing, remember, this is a quantity. And so I'm thinking, does x plus 1 go into 2? Does x plus 1 go into x? And it doesn't. So this expression cannot be simplified any further. I would simply leave it like that. When we're talking about domain and range, remember that the domain of a function are all the input values, all of the numbers that can be substituted in for x. And the range would be all of the output values. Whatever happens when I substitute in for x, whatever number appears is going to be part of my range. The only thing I have to be really careful of when I'm dealing with domain is there are certain times that a function won't exist. So for example, if you think about square roots, if you have an expression like the square root of x, for example, well, I know that I can't take the square root of a negative number. So I would have to restrict the domain to say that x has to be greater than or equal to 0. And likewise with fractions, if I'm dealing with an expression like 1 over x, if you've ever encountered dividing by 0 on your calculator will give you an error message. So if I've got an expression like that, I know that x cannot equal 0. This is what we call restricting the domain. And we'll talk a lot more about this during the year. But I did just want to kind of give you a little preview. There are certain times when our domain is going to be restricted. And usually, you know, with linear functions, with quadratic functions, even with exponential functions, we can plug any number in for x. We say that the domain would be all real numbers. But there are certain functions where our function doesn't exist, and so we have to restrict the domain. The only time we're really going to have to worry about doing that is with division in this case. So in this case, since I've got the 2x on top and the x plus 1 on the bottom, because I'm not allowed to divide by 0, I've got to make sure that this expression does not equal 0. And so off to the side, I'm going to say, okay, so x plus 1 is not allowed to equal 0. If I subtract 1 from both sides, then I know that x cannot equal -1. And so all I'd want to do is put a comma here and just kind of note that x is not allowed to equal -1. And like I said, this is something that we're going to get into later in the year. I just wanted to give you a quick preview. So our basic operations are pretty straightforward. Here are some examples, and what I'd like you to do is to go ahead and pause the video and to go ahead and perform these basic operations on the given functions. Okay, so here are the answers, and this obviously is very similar to the problems that we just did. Notice when we're adding, we don't have to really worry about changing anything. The grouping symbol doesn't make a difference, but with subtraction and with multiplication, it does. And again, notice in letter D, because we're dividing and we have an x in the denominator, we do have to ensure that our denominator cannot be 0. And so we want to set x plus 1 so it's not equal to 0 and solve. And so the only condition for this function is that x cannot be -1. Another thing that we're going to want to be able to do is something called function composition. And function composition involves substituting one function in for the independent variable of another. And we do function composition a lot of times when we're performing multiple operations, and I can kind of probably come up with a good example. If I'm dealing with like going shopping, for example. Let me actually do this on another page. Let's say I'm going shopping and I find a dress that is worth $50. And it's on sale. And it says that it's, let's just make it easy and say it's 50% off. Actually, let's make it 10% off so that we don't get confused. Okay, so it's on sale for 10% off. And let's say I have a coupon for $5 off. Okay, so in a situation like this, the company or the store that I'm purchasing may take the sale price and then evaluate the coupon. So for example, if I'm just looking at a function representing the sale, and if we talk in general terms, I'll call the dress, I'll just say that it's X dollars instead. I want to talk in general terms. So the sale function might be, I'll call that S of, I'll go ahead and call it S of X and say that's going to be X. Now I want to take 10% off. So if I do that, I'd be subtracting 10% of the price. So the original price is X, and then I want to subtract 10% of that. And so again, when we're dealing with percent, you always want to change it to a decimal. Another way of expressing this is to say, okay, well, if the dress is 100%, okay, so let's say the original price is 100% of the price, and I am taking 10% off, that essentially means that I am paying for 90% of the dress. And so if I express, I mean, basically I have common terms here. The coefficient in front of this x is a whole 1, and if I want to subtract a 0.1x, then I end up with a 0.9x. And that just is saying that because I've taken 10% off the price, I'm paying 90% of the value of that item. So then let's say I have my coupon. So with my coupon, I might then say, let's call that C, and so I would maybe take C of S of X, because I'm going to take my coupon off after I've gotten the sale price. So that would be basically looking at S of X minus 5. And so whatever the sale price was, I'm going to subtract another $5. And so this is what we call function composition. It is substituting one function in as the independent variable for another. And so when I do that, because S sub x is equivalent to 0.9x, I end up with 0.9x minus 5. And so we actually do function composition all the time. We just don't always write it out and use the notation that you're seeing here. So let's go back to function composition and what it looks like. If I use our basic function notation where I'm using parentheses, instead of saying f of x, I'm saying f of g of x, where instead of having an input as a single number, I'm replacing my input with an expression. Another way of expressing function composition is using this symbol here. And that's not a cute way to multiply. It's not saying this is f times g, and this is just a cute multiplication symbol. That open circle represents of, and this is basically saying f of g of x. Okay, some people like to call it fog, but it's basically function composition. We always start with a function on the outside, and that's the pattern that we follow. So for example, if I'm using my functions f of x is equal to 3x and g of x is equal to 2x minus 1, in the first example, I'm taking my function f of x, which is 3 times x, but instead of writing x, I'm replacing it with g of x. And so what I like to do is to actually write out the skeleton of my original function and then in a different color put the other function within it. So I am replacing my input with the g function, or simply saying I'm taking 3 times the quantity 2x minus 1. Okay, and so now I can simplify. 3 times 2x is going to be 6x, and 3 times negative 1 is negative 3. And so that's what my new function is going to be. I don't always have to start with f, though. If we look at example 2, we've got g of f of x. That means that I'm starting with my function g of x. And so what I'm going to do is I'm going to write out my function g of x, which is 2 times something minus 1. But I'm replacing that input with my function f of x, and my function f of x is 3x. Now in this case, I don't have to distribute all the way through because the only things that are being multiplied are the 2 and the 3x. So I get 6x minus 1. So notice it's a little bit different. I can also evaluate my function. So if I wanted to find g of f of 2, the easiest thing to do would be to evaluate f of 2 first. And so I'd say f of 2, if I go back to my original f function, is going to be 3. And instead of using an x, I'm replacing it with a 2. So f of 2 is 6. And so then what I'm going to do, if I'm trying to find if I'm trying to find g of f of 2, then ultimately I'm trying to find g evaluated. Since f of 2 is equivalent to 6, I want to figure out what g of 6 is equal to. And so if I plug the 6 into my g function, I get 2 times 6 minus 1. And 2 times 6 is 12. If I subtract 1, I get 11. You could also go back up to your g of f function, which we have here. And if I plug a 2 into that equation, I get the same thing. 6 times 2 minus 1 is going to be 11. So you can evaluate it either way. We can also substitute a function in for itself. So if we take a look at number 4, notice I'm using the other notation for function composition, f of x. So that means I'm taking my function f of x, which is 3 times something, and I'm replacing it with itself. So I'm going to put a 3x inside. And when I do that, I get 9x. And so that is your basic function composition. So attached, you'll find some practice problems on the different operations. They're not all going to be linear, so it'll give you some practice with adding and subtracting and multiplying polynomials and quadratics. But I hope this was helpful.